Happy to welcome you all to the inaugural session of the IISc Outreach Initiative. I am pleased to introduce Professor Arvind Professor of Mathematics at IISc Bangalore. Briefly to speak about him, he's graduated from the Rutgers University with a PhD in mathematical physics, and curiously even his MSc is in math physics from IIT Kanpur. His interests are probability, combinatorics, and mathematical physics. Please.
Thank you. I don't think I need it. Can you guys hear me at the back? Okay. So. Okay. So what I was thinking for today was to tell you some things about what I do. So the plan for the day is that I will initially describe some problems and how to tackle them, and then we'll form groups and I'll give some exercises, and then we'll do them together maybe, and then towards the end I'll tell you about how some of the things that I talked about are related to current research in mathematics. Okay, so the plan. Can you guys see this, or is it too dark? You can see this. Okay. So the plan. So it's in three parts. So first I'll introduce the topic, which is enumerative combinatorics. And then I will describe a specific aspect of graph theory, if you like. Is the study of perfect matchings. So I'll describe this, and in the last part there will be a presentation on tilings. So this is related to this issue of perfect matchings. So if you can't see, you should tell me, because I'll change the. I think it's not dark enough. Okay, so. Answer. I think this is better. So. So let me first introduce the topic. It's okay. I think this writes better. Okay, so it's fine. Okay, so let me introduce the topic. So enumerative combinatorics is really one of the oldest aspects of mathematics. In fact, it's so old that many people think it's not highbrow enough. So it's simply the science of counting. So if you want to think of a general kind of problem, you can say, and I'll come back to this later, if you have n men and n women, in how many ways can they marry each other? Right? So you have guy 1, guy 2 and so on the left hand side, and you have girl 1, girl 2 on the right hand side. There are n guys and n girls. In how many ways can they all be married to each other? No, that's not right. We'll see the answer later on. It's not n squared. It's much larger actually. Okay, so this is the kind of question that keeps coming up repeated again and again in all of mathematics. And so the point is really that we need a systematic. it's a systematic study. Okay, I mean, the point is that for this particular problem that I gave you, you might be able to come up with a clever solution by some trick, or but for a general problem. So here's another problem. You all know what a set is, right? So how many subsets are there of the set 1 through n? You have the set 1 up to n. How many subsets are there? So this is another kind of question that you might or might not know the answer to. But whatever, whether you do or you don't know the answer, that's not the point. The point is, how do you derive it systematically, right? So we need an algorithm, a method to systematically for any problem to tell us how to count. And in mathematics, we are not interested in one particular problem. So for example, this is here's a question. So example, so as I said, the number of subsets of the set 1 up to n for n a positive integer strictly greater than 0. So does everybody understand this notation? Yeah, so this is the set 1, 2, 3, etc. up to n, and this is where n is a strictly positive integer. Okay, or if you want, put natural numbers here. Okay, it doesn't matter. So this is the kind of question. What is not an example? So you might say, okay, everything falls under that, but this is not. So this is an example of the kind of thing that one is generally not interested in mathematics. The number of Sudoku puzzles. You know, everybody knows what Sudoku is. You have this 9 by 9 grid, and it's divided into 3 by 3 grids, and you have to fill the numbers 1 through 9, such that there is only 1 1 in each row, each column. I mean, each row, each column, and each 3 by 3 block. Right? That's what a Sudoku puzzle. So this is one particular problem. I mean, this is not a family of problems. So this is the kind of thing that one is not usually interested in. This is not an example, and this is the kind of example that one is interested in. So what do I mean? So we are usually interested in counting let's say sets or collections let's say families of collections dependent on n on a positive integer n, and one is interested in many kinds of aspects about these questions. Can we get an exact formula? How does it grow as n becomes very large? These are the kind of questions that one is interested in, and you will see more about these things. By the way, if anything is not clear, please ask questions. Okay, so I'm happy to answer. So so the other, so I already said this, and so we don't want a particular trick. So in other words, contrary to what you might think, we don't want to be clever. We don't want a smart solution, okay, for a particular class of problems. We want a generic solution, a generic algorithm. So we do not want a clever solution to a particular problem. So this has several reasons. One is that we want to be able to apply this to as many problems as possible. So one clever idea would work only for a restricted class. But more than that, we also want to quote unquote teach the method to a computer. Okay, so since the last 2 decades, there has been a great amount of research in how to teach computers to prove theorems, not check. Okay, I want you to appreciate the difference. So there are now algorithms, there are programs that can prove certain kinds of theorems rigorously, completely rigorously. Just, I mean, the computers can do it completely. There does not need to be any human intervention. So if there is a generic method, you can write a program and you can encode it as a piece of software, and then the computer can do it for you. That's the point I'm trying to make. If you have a clever solution, then it doesn't work in general, and then the computer is stuck. Okay, so that is the point. So is the broad idea clear? Okay, so so before I describe the algorithm, let's do one particular problem. Okay, so I'm going to describe a problem, and we are going to do it completely, and maybe some of you already know the answer, but and this is related to this. We are going to do this completely, and then we are going to state how to then we are going to look at other examples. Okay, so that's the plan. So let's start with one example. So question, so let me divide the board into. So question, how many non-empty subsets let me write it differently. How many subsets of 1 up to n are non-empty? Okay, so in general, this is the kind of question that one encounters, where this is the family of collections which all depend on n, right? Which depend on n. So as n grows bigger, how many are there, and so on. So how do you approach such a problem? So I want to hear some ideas. I mean, if you already know the answer, keep it to yourself. I don't want to hear your clever answer. Okay, some of you might know the answer already, but that's not the point, as I said. So how do you approach such a problem? Yes?
We can take, let's say, set containing 1 element, 2 element, 3 elements.
Okay, very good. So good, enumeration. So let's just see how it looks like for small. So let's see n equals 1. So the set is 1. So how many non-empty sets are there? No, for this 1. Just this set 1, right? Okay, n equals 2. So this is my set 1, 2. How many non-empty sets are there? Okay, what are they? Right, 1, 2, and 1, 2. So let me write the. So let us call this thing an. So this is 1 here. This is 3 here. Maybe let's do one more. Now you tell me. As before. 1, 2, and 3. Then 1, 2, 1, 3, 2, 3, and 1, 2, 3. 7, right? So already this gives you some idea. So what is the guess? So now that we have done so much work, let's see if this has a natural pattern. So let's see what the guess is. What is the guess?
4 n minus 1.
Exactly. So the guess is absolutely right. 2 to the n minus 1. So the earlier question that I asked, how many subsets are there of 1 through n, is exactly 2 to the n, because the empty set is included. Okay, but never mind. So the question is, how do you prove such a thing? Okay, now for this particular problem, maybe you can think of quick ways to prove it, but we don't want to do that. We want to do it systematically. So the idea is recurrence or recursion. So we want to do things recursively. So let what is my notation? Yes, so let Sn be the collection of subsets of non-empty subsets. Of 1/3. And I am going to, as I wrote here, so and An is going to be the cardinality of Sn, right? So this is my notation. So so we are going to count the cardinality of Sn, or we are going to try to give a formula for An. So recursion is the idea of counting something of size n in terms of smaller objects. So you want to be able to express An in terms of smaller a sub j's maybe, okay? And you want to do it in the simplest way possible. We don't want to complicate our lives too much. So we want to do the simplest possible thing. So let me tell you how you would, one natural way to do it. I mean, you can come up with your own ways, but if they are right, you should all get the same answer. So let An be the subset of Sn which consists, let An of all subsets which contain n. Okay, so each subset in An is a subset which contains n, and Bn those which do not. Right? So Sn is An union Bn. Right? So this is clear. So now how do you, so let's see what the cardinality of Bn is. So let's go back to the examples. So the examples help us. So let's look at the largest example. Which are the things that belong to B3? One, two, 1, 2. That's it, right? So these are the things that belong to B3. Do you notice something special about them? What is B3 equal to? No. Very good, very good. When n equals 2, it's what? Right. So what is my notation? So Bn is equal to, by definition, no, not An minus 1. You're, think simpler, yeah. B3 is equal to all the subsets here. So it's equal to S2, Sn minus 1 in general. Right? Not An minus 1. It includes all subsets of n minus 1 are in Bn. Right? Because the only thing extra in Sn compared to Sn minus 1 is the element n. And if you don't have that, then well, it's just an element of Sn minus 1, right? I shouldn't say by definition. Well, say maybe clearly. So clearly, Bn is Sn minus 1. Is everybody clear about this? Is there any question? Okay, so this part is easy. Okay, so the cardinality of Bn is the cardinality of Sn minus 1, which by definition, which by our notation is An minus 1, right? So one part of Sn we have already taken care of. Now we want to take care of this other part. So let us look at, so this part is B3, this remaining part is A3. Now what can you tell me about, just like we counted Bn, what can you tell me about An? Just by looking at this example, maybe you want to look at this example also. So what is special, what is common to all these elements here in A3? So this, thank you. Oh, A3, I'm sorry. Right. So 3 is common, right? What happens if you remove that 3? Almost. No. Because of the empty set. We don't want this. So since each element, each set in An contains n, there is a one-to-one correspondence between An and Sn minus 1, in the sense that you can get from any element here to any element here, and any element here to any element here, except for the set n. So let me write this differently. So okay, let me write it here. So except for the set which contains the singleton set which only contains n, right? So what does that tell you about the cardinality of An? Sorry? An minus 1 plus 1, because this is the cardinal, okay, maybe I write it in 2 steps. So this is the cardinality of Sn minus 1 plus 1, which is An minus 1 plus 1, right? So what do I have at the end of the day? So thus the cardinality of Sn, which is An, is equal to An plus An minus 1 plus An minus 1 plus 1, which is 2An minus 1 plus 1. Okay? And this more or less solves our problem to some extent. Okay. So this so An equals this. So this is the formula, but one has to be clear when this is valid. So this is called a recurrence relation. And this is what, I mean, morally speaking, we have solved the problem, because okay, so maybe let me finish this point. So this is a 2, yeah. So this is not complete. Why is this not complete? Have you written programs? So have you written programs involving recursion? What is remaining? What do you need for to make the program complete? Thank you. The initial condition. So you need the initial condition. It's not true that A0 is twice A minus 1 plus 1, right? It's not true. I mean, we don't even know what A sub minus 1 means, right? So we have to define the initial condition. So you whenever you have a recursion, you have to be careful about when it is defined. So for what values of n is this defined? So does it hold for n equals 1? So if what is the statement for n equals 1? That would be A1 equals twice A0 plus 1. Do we know what A0 is? Well, if you wish, we know it, because the n equals 0 case is the empty set. How many non-empty subsets are there of the empty set? 0. So here this is 0. So it does hold for n greater than or equal to 1. Yes, this is true. But as you said, we also need the base case. If A0 were 100, then that would change our answer completely. So we need to know what A0 is with A0 equals 0. Okay. So this is the complete information about the recurrence relation. Okay, it's just, have you seen differential equations? So you know, for a differential equation you also need the initial condition or the boundary value. You know, so depending on the kind of initial kind of differential equation. So why am I claiming that this is, we have morally done our job? Because if you do not know anything and I ask you what is the value of A sub 100, the brute force way of doing it is to just list everybody out and then count them, right? And that's a tremendous amount of work. I mean, 2 to the 100 is a huge number, right? There is no way you can count it. But with this algorithm, you can count it very quickly. In 100 steps you can count it actually, okay? A little more. But because if you store all the values of the lower guys, you can count this very quickly, okay? So this is not a complete answer in the sense that it's not the best possible answer in the world, but a computer can calculate with this extremely fast. So if you need to calculate A sub 1000, you know, it will do it for you very fast. I mean, of course you have to write the program properly, but modulo that, we have in some sense solved the problem. But I am going to tell you a better or a more refined approach, starting from this point. So usually when you have these problems, you find a recurrence which may be the best recurrence in the world. Okay, so there are several possible recurrences for the same problem, but I don't care. I mean, we want one recurrence, and from that we'll be able to solve it. Okay, so the main idea now is what is called a generating function. Okay, so have you guys seen generating functions before? No. Okay, very good. Okay, so this is something new. Okay, so pictorially, or yeah, so maybe let me just write this. So a generating function is like a clothesline. You guys have seen this, you know, where you hang your clothes, you know, it's this line where you hang your sequence up for display. Okay, so this is just some you know, visualization scheme. So given a sequence, so let me define that now. So given a sequence AN, the generating function A of x is the sum n greater than or equal to 0 an x to the n. Okay, so what you do is you create a function of x by writing down like a Taylor series, like a series expansion. So in our example, in our problem, A of x is 0 plus 1 times x plus 3 times x squared, right, plus 7 times x cubed plus etc. Okay, so you know, it's an infinite series, but that should not well, okay, so there is something to think about there, but let's not worry too much about it. Okay, so is the idea of a generating function clear? So you write an expansion, you write all possible powers of x, and adjacent to the particular, each power has the coefficient equal to the value of our sequence. Okay, that's the idea. So shall we see an example? So this is something you have seen before. Consider the sequence So this is an example. an equal to 1 for all n. An is just the simplest sequence you can think of, non-zero sequence you can think of, which is just 1, 1, 1, 1, 1, 1, 1. It's 1 forever and ever. So what is a of x? So a of x will be 1 plus x squared plus etc. all the way. Have you seen this before? What is this? Exactly. This is the geometric series, which is 1 by 1 minus x. Okay. So the generating function, so notice what we have done now. We had a discrete object, which is the sequences, right? These are just numbers now, one number at a time. And from there we have gone to a function. And the beauty of generating functions is that by analyzing this function, you can say a lot about the sequence. You can okay, it's a bit early in the game, but you can say a lot. You can give a lot of information about an by just doing analysis on this function. You can, for instance, try to see where its roots are, and you can get some information from there. You can also you can also calculate more probabilistic things like the average value of the sequence and so on. Yeah, there are lots of things you can do. Okay, so let me keep this recursion. So we are going to try to calculate a formula for an by looking at its generating function. That's the strategy. Okay. All right. So okay. So let's start the following way. So let me rewrite the recursion a little differently. Let me shift the index. So let me write it as an plus 1 is equal to twice an plus 1. Now, because I have shifted the index, so this is true for n greater than or equal to 0, right? And a0 equals 0. Okay. So now, so let ax be as before for this sequence an x to the n. Okay. So what I'm going to do now is multiply by x to the n on this in my recursion, or rather on the for the left hand side, and sum. So consider, so since I already have the recursion, I'm going to delete this, erase this with that. So n greater than or equal to 0 as before, an x to the n, an plus 1 x to the n, I'm sorry. That's the left hand side here. No, no, it has to be x to the power n, yes. There are other kinds of generating functions, but maybe I can tell you later. Yeah, that would be an unnecessary distraction. Okay, so we are, so I want you to think about how this is related to a of x. A of x is an x to the n. How is this guy related to a of x? So let's do the expansion. So I have a1. So this, let me show you what this is. So this is a0 plus a1x plus a2x squared plus etc. Correct? Now this is my first index when n is 0 is a1 x to the 0, which is a1. Then I have a2x plus a3x squared. So it's shifted by 1. How do you write this thing in terms of this thing? Almost. Very good. Yes. Does anybody else see it? Now let others answer. Sorry? Minus a0. Very good. So this is equal to a of x. So if I take a of x, let me write the whole thing. Let me write a of x. So this is a0 plus a1x plus a2x squared, etc. all the way minus a0. So that takes care of the first, the 0th order term. And now everything has an extra x factor. So I can divide by x. Is this clear? If it's not clear, please ask. Now this thing is my a of x. So this is a of x minus a0 over x divided by x. But a0 in our example is 0. So this is a of x by x. Okay? So a of x by x is equal to sigma n greater than or equal to 0 a n plus 1 x to the n. I am just writing it again. So far I have not done anything. Now I am going to use my recursion or recurrence. So this is sigma n greater than or equal to 0 twice a n plus 1 x to the n. Remember that this holds for n greater than or equal to 0, so I can substitute it in each term. Otherwise I would have to be a little careful. Okay, there is a it's not valid for a0, that's why I shifted the index. Okay, and now what is the first term? Does everybody see this? Okay, you guys can't answer. Let someone from here answer. What is the first term here? This is just 2. So this is 2, I can remove, so I will split it in 2 terms. A n x to the n plus the second term is simply x to the n, right? So what is the first term? Simply twice a of x, right? I get back a of x. And what is this term? Have you seen it before? Yeah, it's just this. This is the same thing. This is 1 by 1 minus x. So ax by x is twice ax plus 1 by 1 minus x. So let's do the algebra. So a of x is 2x a of x plus x by 1 minus x. Yeah. So okay, I leave it for you to do the exercise. So this is x by 1 minus x, 1 minus 2. Okay. So I got an explicit expression for my generating function. Okay. So this is an even better answer than the recurrence relation, because I have now a really very explicit formula. Okay. Any questions about this step, this calculation? Okay. So the last stage of this is to get a formula for an. So if we can do that, all the better. That would be our ultimate solution. But this is already good enough for many practical purposes. So at the first level, you have a nice expression in the sense, you have a nice answer in the sense that you have a recurrence. Now you have a nicer answer in the sense that you have the generating function. And now I will give you the nicest possible answer, which is an explicit formula. So how do you do that? How do you get an explicit formula? Does everybody know partial fractions? Okay. So let's do partial fractions. So x by 1 minus x, 1 minus 2x is a by 1 minus x plus b by 1 minus 2x. So this is partial fractions. You will see why this is useful in a second. So what is a and b? Can anybody do this quickly? Actually, let's do this way. Take the x outside. So I want, so x times 1. So do the partial fractions for 1 by 1 minus. This is minus 1 and 1. No. So A is minus 1, yes, I think I agree. So if this is 1, then things don't cancel, no? A is B is 2. B is 2, yes. The 2x doesn't cancel otherwise. No. I will pull the x out. I'm doing the partial fractions of 1 by 1 minus x. So what happens here? I have 2 minus 2x minus 1 plus 2x. So 2 minus 1 gives me 1 and the 2x cancels. So this is correct. Should I do this? Yeah. So this is equal to, this is just a digression. So this is minus 1 minus 2x plus twice 1 minus x divided by 1 minus x, 1 minus 2x. The x is already outside. Okay. So this is plus 2x, that cancels with this minus 2x. I get 2 minus 1, which is 1. Okay, can I erase this? Okay, let me wait. Okay, so now we are almost done, because we know what the expansion of, what the Taylor expansion or the geometric series representation of each of these terms is. That is the point. So let me write this. So this is 2x by 1 minus 2x minus x by 1 minus x. So this is equal to 2 I can take outside, 2x I can take outside. This is sigma n greater than or equal to 0, 2x to the power n, right? 1 by 1 minus what? 1 by 1 minus blah is sigma blah to the power n for summing over all n, right? And I'm just replacing x by 2x, right? So what 1 by 1 minus y is sigma y to the n. So put y equals 2x and you get the first term here. I've taken the 2x outside, okay? Minus x times x to the n, right? Okay. So I have in common, and so let me combine both these terms. So I have x to the power n plus 1 in both cases. So I have 2x to the power n plus 1 minus x to the power n plus 1. Yeah. So this is sigma n greater than or equal to 0, 2 to the n plus 1 minus 1, x to the n plus 1. But what is Ax? Ax is, by our definition, this is equal to sigma n greater than or equal to 0, an x to the n if you wish, or an plus 1 x to the n plus 1, doesn't matter. A0 is 0, we know anyway. So this implies, so but Ax is equal to this, so this implies an plus 1 is this, or an is 2 to the n minus 1. Okay, so this is what we start, this is what we guessed, and this is true. Okay. So we went through a long series of calculations to get an answer that we already knew, but there was a point to this, and that is that if I give you another sequence for which you can't guess an answer, you can at least do these steps. Hopefully you will be able to do these steps for a general problem. Okay, so that was the idea. So so let me list down the steps, and then we'll proceed to the topic that I wanted to discuss. Okay, are there any questions before I list the general steps? So, okay, let me write it down. So, general steps. So suppose our sequence is AN. So the unknown sequence is AN. Oh, sorry, little an. Okay. So first step is to find a recurrence, and this is usually the most creative part of the whole process. Okay, you remember I had to break the set Sn into two parts, depending on whether the subsets n belong to the subsets or not. So you might have to break, given a problem, you might have to break it into several different classes, and you might have to deal with each of them separately. It's possible that things can get complicated, but this is usually so. If you have done this, then you are already more than halfway done. Find the a recurrence. Any recurrence is okay, and you have to be careful about the range in which it works, and then you also have to find the initial condition. There could be more than one initial condition that you might need. Okay, so it's possible that you need A0, A1, A2, A3, and then you can give me a formula for A4 up to all the way up to all the way in terms of the lower ones. So define. So once you have the recursion, that's a lot of progress. So define the generating function a of x. So expand a of x using the recurrence. And solve. So you'll get an equation involving a of x itself. You would have eliminated all the little an's, just like we did at some point, which I erased. And solve for a of x. Now expand a of x using known rules, such as the geometric series expansion. And if you had gotten the answer as e to the x, then also you know how to expand it, right? E to the x is 1 plus x by 1 factorial plus x squared by 2 factorial and so on, to get a formula for an. Right, so we started trying to get an, we went to the function, found a formula for the function, and then went backwards. Okay, so this is a very general, powerful approach that works in many cases. Okay, so let's see. So when should we take a break? Is there any suggestion? It's almost. Should we take a break at 4? 3:30 is okay. Okay, then let me. Okay, then let me start on. So let's see, what should I do? I can give an exercise. 4 is better? Okay, yeah, because that will give me enough time to present the material for the next part. All right. So after the break, we'll do some exercises of this kind, okay, so that you get to see how this works in practice. So now the topic is changing. So there is no cleverness in this whole procedure except maybe in the first part. Okay. So now I want to go into a topic of somewhat current interest, and this is perfect matching in graph theory. Okay. So the starting point for graph theory is, of course, a graph. So let me just define a graph. So everybody hopefully has seen it in some form or the other. So graph G is a pair V comma E, where V is a set, right? So everybody knows what a set is, and of vertices, and E is a subset of V cross V called the edges. Okay, so you take two vertices and connect them by a line which we call the edge. So a graph is simple if there are no self loops. That is to say, a vertex is not connected to itself or multiple edges. So between any two vertices there is at most one line, one link. So here's an example. So here's an example where my V is the set 1 up to 6, and E is something, you know, okay, so maybe I'll write 1 2 1 4 etc. Okay, you can fill in the edge set. Wherever there is a line, you draw, you include that in the. Yes.
So about the general steps that we had, the last step you said expand AFX using node roots to get a formula for AN.
Yes.
So we did that using partial fractions, right?
Right.
So are you saying that every time we get AFX in terms of x, you have to use the partial fraction?
No. For example, so if you have, I mean, so example, A of x could be, I mean, this is not really a sequence of integers, but you know, you could have some variant of e to the x or log 1 plus x. You know, these all are things whose series expansions you know. It could be cosine, sine, it could be all sorts of things, you know. So
in those cases, then our approach to solving to find the formula for AFX would be different.
yes, right. So today all the examples that I have in mind are of the form functions, but you know, in general there could be a lot of things. So of course you could have said if I don't know e to the x, then I'm stuck, but you know, these are things you can find in a table or some such thing. Yeah. So I mean, yeah, so certain amount of background information you do know, and I am assuming that you know. Okay, so here is my here is one particular example, nothing special about this graph. So everybody has seen a graph before, right? I don't have to assume. Okay, so now this you might not have seen. So I'm matching M of a graph G, which is V comma E, I'll always assume G is VE from now on, is a subset of E such that no two edges in M share a vertex. Okay, so I have a bunch of edges. Okay, so here is, suppose 2 3 is in this, then 1 2 cannot be, because if 1 2 were there, they share the vertex 2. which is not allowed. So something else could be there, this could be there. Okay. So this is a matching. You know, there could have been a single edge. That's also a matching. Okay, it's a simple. I mean, because if there is a single edge, then of course no two edges are there to share a vertex. So of course it's okay. But yeah, there could be more like this example. Okay. What next? So this is of course too general, and so next we want a maximal matching. So another definition: a matching is said to be maximal. A matching M, let's say, is said to be maximal if the addition of any new edge to M let's see, yeah, okay, let me just write it properly. Makes it no longer a matching. I mean, I have not said it in the best possible way, but the point is that if you add any new edge, then they will share a vertex. Is it not? Okay. So this is not a very good example for me. So this is not a maximal matching. Why? Sorry? Why is this not a maximal matching? Which edge can I add? 1, 4 I can add. So I want to disallow that. So what I'm going to do is I'm going to add 4, 5. This is a maximal matching. Right? So if I can't add 1, 2 because 2 is already there. I can't add 2, 4, both are there. I can't add 1, 4, 4 is there. Can't add 5, 6. So this is a maximal matching. Oh, but it's not what I'm going to write next. A matching M is said to be maximum if it has the maximum possible number of edges.
This one is not unique. Maximal matching.
Maximal matching is not unique.
Is this unique?
No, this is also not unique. For this graph, well, okay, yeah. So let me come to that. Yeah. So is the matching that I have drawn in blue a maximum matching? It's a maximal matching, but is it a maximum matching? Why? Because the earlier example had 3 edges, and here I have only 2 edges. So let me go back to this thing. So if I want a maximum matching, this has to be connected. Then 3 cannot connect here, so 3 has to connect here, and then this is connected here. Right? So this is a maximum matching now, right? So a maximum matching. So but what does this example tell us? A maximum matching is always maximal not the other way around. Because we saw maximal matching which was not maximal, right? Clear? Okay. So, what is the maximum possible number of edges in the maximum matching? So, what is the number of edges in the maximum matching equal to? Very good, almost right, but not quite. Okay, so good. So now let me give an example where what you are saying is not true. Consider this. So give me an example of a maximum matching. What is the max? Give me one example. There are many. 1, 2 and 1, 2 and 5. What? 5, 4. Okay, that is a maximum matching. Yes, that's certainly a maximum matching. 1, 2 and 3, 4 is also a maximum matching, and it's also maximal matching, of course, right? So your formula is almost right. What makes it wrong? For exactly. So the number of edges in a maximum matching is the cardinality of V divided by 2 if V is even. Well, you have to be assuming it's connected and so on. So there's some assumptions. But if it's V cardinality of V is odd, then V by 2 is not an integer, and you take the floor or the greatest integer. Yeah, it's simple. All right. Yeah, this actually, well, okay, so let me put this in quotes. You have to be a little careful. Okay, this is not always true. All right. So the last definition, before maybe I can put it over there. So last definition is that of a perfect matching. So a perfect matching of a graph, okay, is a matching in which all vertices are matched. Okay. So a perfect matching is one where every vertex is connected to some other vertex, and because no two edges can share a vertex, if a vertex is connected to some other vertex, it's not connected to any other vertex, right? So you see, so in particular, perfect matching exists only for even length, even number of vertex graphs. Okay, is that clear? So
as an aside,
yeah.
I think this has got some relation to what they call the stable marriage problem.
Yeah, right. Of course, yes. This is very much related to the Hall's stable marriage theorem. Yes. Good. But yeah, I'm not going to talk about that. Okay. That won the Nobel Prize last year in economics. Shapley, I think Shapley won. Okay. So okay, very good. So let's see some examples. So let. Oh, sorry. So let Pm of G be the number of perfect matchings of the graph G. Okay, so this is the notation. So my first class of examples is the following. So let Pn be the path graph. So so 1 is connected to 2 is connected to 3, etc. all the way is connected to n. Okay, so it's just one single line. So what is Pm of Pn? How many perfect matchings are there? Oof, not even close. That's getting closer. N by 2, no. It's a perfect matching. N minus n by 2 is n by 2. Sorry? N minus 1. No, I'm saying you're not even close. Yes? Perfect matching is a matching in which everybody is connected to everybody. I mean, everybody is matched. There's nobody. This is not a perfect matching because 3 is left hanging. Very close. So she is saying 1. You're almost right. So let's look at an example of 4 vertices. P4. What is the perfect matching? 1, 2 and 3, 4. Okay. Now let's look at P3. Huh? 1 is connected to, what is the matching? What is the perfect matching? Not possible. Why? Odd numbered. Yeah, because perfect matching everybody has to be matched. So it's not possible. So at least that gives us one. It's 0 if n is odd. What is it if n is even? So 4, what is it for 2? 1. For 4, it's 1. It's always 1. It's always 1. If you want, do it inductively. Here is my, so let's do it this way. So Pm of P sub 2n, right? You will, 2n always has to be matched to 2n minus 1, right? The end always has to be matched. So this is equal to Pm of P 2n minus 2, because 2n has to be matched to 2n minus 1, right? Isn't this clear? This guy at the end has to be matched. So if this is matched, I can kick both of those two out and I'm left with a smaller graph, which is 2 smaller and has the same number of perfect matching. Because whatever is a perfect matching here is a perfect matching here with that extra vertex, but there's only one here, so this is one. Because P2, P2 is 1, so P4 is 1, P6 is 1, P8 is 1, all the way. It's an inductive argument, right? Is this clear? It's a path graph, so and we want perfect matchings. So the ends have to be matched, and that will force things iteratively until you're stuck. For an odd case, if you start at the ends, you reach a contradiction because you find a vertex which is connected to 2 edges, which is not allowed. Right? For even cases, it is consistent. You can start from both ends, and you will reach. You'll exhaust everybody. Yes. So Pm of Pn is 1. right? What about maximum matchings of Pn? This is not really, this is an aside. What is the number of maximum matchings of Pn? So on the other hand, number of maximum matchings of Pn, what is it? N by 2. I don't understand how you are thinking. But yeah, no, it's not N by 2. It's a maximum matching. It's again 1, almost. If n is even, it is 1, because a perfect matching is also the maximum matching. If n is odd, it's 2. Very good. So look at this example, because a maximum matching can either start from one end or the other end. So if I have, so this is 1 if n is even, 2 if n is odd. Very good. Do you see this? So let's do the example for n equals 3 might be too trivial. So let's do this. 1, 2, 3, 4, 5. What are the two maximum matchings? 1 to 2, 3 to 4, or 2 to 3, 4 to 5. Both of them leave exactly one vertex and you cannot add anymore. Oh, well, maybe I made a mistake. Yeah, I can also do this, right? No, so maybe I'm wrong. 1 to 2, 4 to 5 also. No, maybe I'm wrong. Maybe it is wrong. Okay, forget it. Let me take this back. Yeah, maybe it is n by 2 minus 1 or something. Okay, sorry. Yeah, I take this back. Anyway, we can think about it later during the exercises. Okay. So let me come back to something related to the stable marriage problem, but only related. And then we can take a break. So a bipartite graph G is one in which the vertex in which V can be partitioned into two classes, into two subsets, let's say V1, V2, right? So that you can break the vertex set into two parts such that every edge has one vertex in V1 and one in V2. Another way of saying it is that there are no edges between vertices of V1 themselves and those of V2 themselves. Okay. Is the definition clear? Let's see an example. So is this a bipartite graph? I want to divide my vertex set into two blocks. They don't need to be of the same size in general, such that there are no edges connecting things within the same block. So is this bipartite? Okay, what are the things? What? 1, 4 and 2, 3. So V1 is 1, 4, V2 is 2, 3. So 1 is connected to 2, 1 is connected to 3, 4 is connected to 2, 4 is connected to 3. There is no 1, 4 or 2, 3. So, this is bipartite. Right? But this is not, right? Because now 2 is connected to 3, so that you cannot find any class which does not talk to any of the other class. It's not possible to divide. Okay, this is not a bipartite. Okay, so maybe a couple of more definitions. So the complete graph, as you might guess from the name, the complete graph Kn is the graph with v equals 1 to n and the edge equal and all possible edges. Let's say. So every vertex is connected to every other vertex. Okay, it's called the complete graph. And the complete bipartite graph on vertex sets V1 and V2 is the graph where every edge, every vertex in V1, oh, it's not visible. So every vertex in V1 is connected to every vertex in V2. Okay, because it's bipartite, there are no vertices between V1 among the vertices of V1 separately and V2 separately.
I think we should mention that every example of a graph is a simple graph.
I said simple graph. I'm only talking about simple graphs, yeah. And I haven't defined what a directed graph is, but there are no arrows on my edges. So my edges are just lines. Okay, they don't have any direction. So they are called undirected graphs, if you like. Okay, so let's do my example that I promised at the beginning. So V1 is 1 up to n, V2 is also 1 up to n. Okay, so if you want 1 prime and prime, so I have, so this is, by the way, a complete bipartite graph, right? Because every vertex in V1 is connected to every other vertex in V2 and vice versa. Okay, so now if one natural way to express these things is to write V1 on one column, V2 in one column, and connect them. So V1 is 1 to n and V2 1 to n, maybe call it 1 prime 2 prime up to n prime. So and complete bipartite graph. So this 1 is connected to 1 prime 2 prime etc. up to n prime, 2 is connected to 1 prime 2 prime etc. all the way up to n is connected to 1. So it's a horrible looking graph. I mean, there's many edges. Okay. Now the question. So let's call it something. What was my notation? I called it something. Bn. So Bn is my. This is my graph Bn. Okay. It has 2n vertices and lots of edges. So maybe you can tell me how many edges there are. I think it's n squared. Yes, n. Yeah. Right. It has n squared edges. So the question. So this is the. Can you see this related to what I said in the beginning? You think of V1 as a list of n men, and V2 as a list of n women, and the number of perfect matchings of Bn is, what is it? It's exactly the number of ways they can all be married to each other. I mean, each other meaning men can be married to women. So okay. So what's the answer? Let's do an example. Huh? Anybody has a guess? So let's do 3. 1, 2, 3, 1 prime, 2 prime, 3 prime. So all the edges are there. I'm just.
Is it number of surjections?
Something.
Number of surjections.
There's a simpler way to express it. I just let me just do the example. So 1 can be matched to 1 prime, 2 can be matched to 2 prime, etc. There cannot be any connections here. Remember, there are no edges here. 1 can be matched to 1 prime, 2 can be matched to 3 prime, and 2 prime can be matched to 3. Okay. Now I won't write 1, 2, 3. 1. You can see what it is. 1. Oh, this is 2. Sorry, 2 prime. Sorry. So this, this, and one more. This. So if 1 is matched to 1 prime, then there are 2 options, right? 2 and 3 can either be matched to 2 prime and 3 prime in both ways. 1 is matched to 2 prime, again there are 2 options. If 1 is matched to 3 prime, again there are 2 options, which is 6. N factorial. Thank you. This is n factorial. So how do you prove this? So you consider what n is matched to, okay, and remove it. Then you have n minus 1 edges, vertices on this side, 1 through n minus 1, and you have n minus 1 other edges on this side, not 1 prime through n prime. You have something removed, but there are n minus 1 of them, and so what we can show, the recurrence here is Pm of Bn is n times Pm of Bn minus 1, right? And then this is equal to n minus 1 times Pm of Bn minus 2, and so on all the way. And we need the initial condition, so Pm of B1 is 1, right? If there's one woman and 1 man, they have to get married to each other. Okay, so that's the. So that proves this. So this proves this. Okay, and let me end with another aside. So a remark. So the generating function here a of x, which is 1 plus x plus 2x squared plus 6x cubed plus etc. n factorial x to the n plus etc. This is well defined as a power series. So this is the kind of thing that we have been considering as our power series as in the generating function language, right? We have sigma a n x to the n is the kind of thing we have been considering. But as a function, this is not well defined at all. In fact, it's the only place it is well defined is for x equals 0. This function blows up, diverges everywhere outside of x equals 0. So if even your value of x is 0.00001, it's going to become infinity if you take enough. I mean, it's going to diverge if you take all the terms. Okay, so this is somewhat of a pathological example, because here one is not you cannot use the functional properties of the generating function anymore. But in most of the examples used in practice, the function is also nice in some domain. For example, so this is not defined for x not equal to 0. On the other hand, whereas 1 by 1 minus x is well defined in a region, in a non-trivial region, which is the region where mod x is less than 1. And so it is, you can treat it as as an honest function, and you can do some analysis on it, whereas you can't do anything for this guy, okay, even though it is nice. And so this is a more pathological example, and this is the kind of example where other techniques are useful, but I am not going to talk about it. Okay, so I think this is a good time to take a break. We'll come back and do some exercises. Okay.
10 minutes.
10 minutes, yeah.
10 minutes.
Any of the examples that we did? Okay. So I want to do 2 examples in let's say half an hour or a little more than that. So I was told that we'll be able to form groups so that I can assign you problems and you can work on them, but I don't know how to do that in this auditorium. But okay, maybe you guys can form, maybe you guys can sit so that you are together with your friends and you guys can try the problems together. I don't know. Can you form clusters like that, or I don't know how to do
Yeah,
it.
we can just count 1, 2, 3, 1, 2, 3. 3 in a group.
No, okay. I think that's a bit too kiddish for them. Okay. Okay, so you remember the generating function approach, right? So I'm going to give you another recursion for which the answer is not so clear. So exercise. So suppose an plus 1 is 2an. We had plus 1 earlier, right? That's the problem we solved, where an was 2 to the n minus 1. But here suppose it's n. Okay. An plus 1 is 2an plus n. You guys can solve it in groups if you like, for n greater than or equal to 0, and a0 is equal to 1. Okay, so the problem is find ax. So the first part is to find ax, and the second part is to find an. So go ahead. I mean, you know the techniques. If you get stuck at any point, raise your hand and I'll come over there. You guys can work in groups if you like. I don't care. Is the problem clear? There any doubts about the problem? So ax is sigma an x to the n greater than or equal to 0. So it's a0 plus a1x plus a2x squared, etc. So what do you get? Has anybody done it? A of x equals what? All right. So, so now that we have done a lot of perfect matchings, I want to show you some more modern applications of these ideas to the problem of counting tilings. So, tilings, and you might be thinking that they are similar to perfect matchings, and you will be right. I mean, I will show you why in a second. So, so I will basically describe tilings of three kinds of objects, and which have a lot of interest. This one starting sometime in the 60s. Actually, hexagons go back in another form to the early 1920s, and Aztec diamonds are more recent, mid 1990s, and I'll end with some notions of probability about how to pick random tilings and what it means. Okay, so here is a tiling problem that that you might want to consider. Here is a region, this funny region over here, and here are these bunch of tiles that I give you. Okay, so it's like a jigsaw puzzle, right? So you are given these things, and I ask you to put it back together, and here is a solution. But why is this not a mathematically interesting problem? And this is a recreational problem, right? I mean, here is a particular figure, and here is a particular tiling of it. I mean, each of you can cut it up into whatever way you like and present it to me, and I could break my head trying to solve it because it could be very difficult. But that doesn't mean it's interesting, right? It's just like this Sudoku example I gave you. I mean, just because you can count something doesn't make it interesting. We are more interested in families of tiling. So, just like number of perfect matchings for a general series of pairs. So, what is the question? So this usual in a usual tiling problem, you have a region and you have a set of tiles, and you are asked to cover the regions using the set of tiles, and usually you can just move the tiles around. You can just translate them. You are not even allowed to rotate them. Sometimes it's possible to ask questions with rotations, but usually not. And you can't cut the tiles. You can't make the problem more simpler by cutting the tiles or doing something else, right? So this is the general question that the general setup, and the questions are the following. Does a tiling exist? First of all, a priori it might not even be clear that such a tiling exists. Suppose that you can show that there is a tiling, then the next natural question, particularly for enumerative combinatorial people, would be how many are there, and if how many are there, you can ask at various levels. Can you find a recurrence? Can you find a generating function? Can you find an exact formula? Even if not, sometimes we are happy if you can give us an approximate formula, something that gets better and better as n goes to infinity. We are usually interested in large tiling, so how many are there approximately is good enough. Can you construct an explicit example? Can you relate the tilings with each other in some sense by doing some moves? That's also a question. Then how about tilings with special symmetries? When we were doing the ladder graph, not all perfect matchings were symmetric with respect to reflection, right? So the all verticals one is symmetric under reflection, but very few else are. So then you can ask the question, how many tilings respect that symmetry? So the last is closer to the first. If no tiling exists, seems to exist. You tried very hard to find a tiling and you are not able to find a tiling. Can you mathematically prove that there is no tiling? That's another question that is often of interest. So here is an example that you might want to consider. You take a chessboard, which is an 8 by 8 grid, and you remove two diagonal blocks from top left and bottom right. How many tilings are there? Using dominoes. So a domino is a tiling with two adjacent blocks. So either vertically or horizontally. No diagonals allowed. Yes. So these are my tiles. These are my set of tiles. This is my region. Oh, I have a pointer. How many tilings are there of this region with these tiles? 4, no. Let's take the sorry. Yeah, you can move. You can take as many copies of this as you like, and you can place them, and you want to cover them exactly. There shouldn't be anything protruding, and there shouldn't be anything left out. They should exactly cover these things. So how many are there, do you think? Huh? What did you say? What do you mean? I'm not considering a family. This is a particular graph. I'm not considering the graph of all possible chess. Right. You shouldn't have anything extra protruding. There shouldn't, at the end, there should not be a domino like this. That's not allowed. It's not possible is the correct answer. Why? No. 64 is the total. Minus 2 is 62. Okay, let me ask you another question. Suppose I removed this and kept this instead. Then it's possible. But if you remove these two, it's not possible. If you can try actually, and you will find that whatever you do, you won't be able to do it. And why? So it doesn't seem to exist. Let's say you worked very hard. For 1 hour you sat and tried to put it, and you were not able to come up with a tiling. Can you prove that there is no tiling? How do you prove that there is no tiling? So that is the correct answer. There is no tiling. And the correct idea, there is a hint, because I called it a chessboard. I don't have to call any 8 by 8 grid a chessboard. So the hint is that the chessboard is not a proper chessboard until it's colored properly. Okay. So let's color it. Oh, you can't see it. So this is supposed to be colored actually. So these are blacks and these are whites. So black, black, white, 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 black, 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 black. Anyway, you can't see it very well here. But the idea is that this is a black and this is also a black. And every domino covers one black and one white. So now, if you wanted to cover the complete chessboard, you needed to have 32 blacks and 32 white squares. But now you have 31 white and 31 black and 33 white squares. So there is no way you can cover it. Well, actually I removed 2. So what do I want to say? 30 and 32. 30 and 32, yes. 30 black and 32 white. So there is no way you can cover, because at the end, no matter what you do, you will be left with 2 black squares. And there is no way that 2 black squares can be spanned by a domino, because a domino covers only adjacent vertical or horizontal neighbors, right? So this is called a coloring argument. So this is actually a proof that you cannot cover this region, right? So this is the kind of question that one is interested in. So the other example, so you might want to think of, is the perfect matching example that we did. So I can't use the board now, but I forgot. So every tiling by dominoes is a perfect matching really. Why? Because I can take the graph, let us just look at this example. I mean, this is not what what we are doing. So, let us look at this 2 by n, 2 by 8 thing, right. So, I am just illustrating the idea. Construct the graph whose vertices are the centers of the squares, okay, and whose edges are vertical and horizontal lines if two blocks are connected by are touching each other. So, this will give me 8 vertices here, 8 vertices here. They are connected, each is connected vertically and they are connected horizontally exactly like a ladder graph, right. So, this is, and if a horizontal tile is put somewhere, that is like a perfect match, that is like matching those two vertices, okay, that is the idea. So, a tiling of this 2 by 8 region by dominoes is identical to a perfect matching of the ladder graph L8, okay, that is the idea. So tilings by dominoes are identical to perfect matchings. Is that clear? I mean, I am not sure I explained this very well because I am not able to use the board, but I hope it is clear that perfect matchings, so any perfect matching of a 2 by 8 graph can be made into a tiling. Wherever there is an edge, I put a domino, and any domino tiling of this 2 by 8 region can be made into a perfect matching of the ladder graph by just putting an edge wherever there was a domino. So, replace edges by dominoes and you get the correspondence, okay. So, that is the idea. So, and this is what I just showed about 5-10 minutes ago, that the number of tilings of a 2 by n rectangle is the Fibonacci number n plus fn plus 1. This is the same as the number of perfect matchings of the ladder graph. That is exactly the same thing, and this is what I showed. This is fn plus 1 because it shifted Fibonacci. Okay. So, now you take a 2m by 2n general rectangular graphs grid, okay, and now the question, people asked the question a long time ago, how many domino tilings are there of this region, okay. So, I am taking 2m and 2n because it is so that to make it even, to make the if both m and n are odd, then the total number of vertices is odd and there cannot be a perfect matching or a tiling. But if both are even, the question is how many tilings are there? There is of course one tiling which is all horizontals, there is one more which is all verticals. So, there it is a non-zero set, it is a non-zero number, and so you can ask how many are there. And amazingly, and this was just an incredible coincidence, in the year 1961, two groups of people completely independently solved this problem. This was unsolved for a very, very long time, and exactly in the same year they both solved it independently. So, one was this English group by Temperley and Fisher and Castelline, who was actually at that time working for Shell, the oil company. So, they showed that this absolutely incredible formula, that the number of domino tilings of this 2m by 2n grid, which is the same as the number of perfect matchings of this grid graph, is given by this formula: 4 to the mn time, this means product over all j from 1 to m, k from 1 to n, cos squared j pi by 2m plus 1 plus cos squared k pi over 2n plus 1. So, you take m times n such factors, okay, and you add them, multiply them out, and the amazing fact is, these things are horrible numbers. They can be, cos squared pi by 17 you will get if m is 8, right. I mean, there is no simple formula for these things. You can get, yeah. So, it's absolutely incredible that not only is this just like this Fibonacci example, not only is it a rational number, it is actually an integer. And let me give you just one illustration. You take the 3, so m equals 3 and n equals 2, so 4 by 6 grid, and you get this horrible expression, and if you get all these numbers which are all irrational numbers, okay, highly non-trivial, and if you multiply them all out, you will get 281. I mean, it's an amazing fact, okay, and I mean, I hope you appreciate how non-trivial this is. I mean, how do you know that, I mean, there's no way you could have guessed this formula, right? Because you would have seen some numbers, you would have guessed, okay, you know, some rational numbers maybe or some such thing. These are trigonometric polynomials. I mean, there's, yeah, so this has spawned a lot of research. Okay, so let's take a very large, so okay, that's one exact formula, okay, and so for such things there is no nice generating function or some such thing, you know, these things are just magical, they just appear like that, you know, and then there's, anyway. So let's take the 40 by 40 grid. So what is drawn, what is taken here? So you can see that these are domino, this is one particular domino tiling. So what we have, whoever, I've taken this off the internet, so someone has done this. So they've taken all possible domino tilings of this 40 by 40 region and picked one at random. Okay, it's just one particular random one. So if you pick something at random, it's very unlikely that it's going to be all horizontal, right? That's like tossing a coin 1,000 times and getting it all heads. That's not going to happen, right? So this is how it looks, and if you look carefully, there's no real structure. I mean, this region over here pretty much looks the same like this region over here, which pretty much looks like this region over here, right? So there's no real structure, and I'll come back to this in a second, okay? But this is what I want you to keep in mind, that there's no real structure. You can't really distinguish. If I cut out this part and I cut out this part and I kept them both next to you, you would not be able to tell me which is on the corner and which is in the center, okay? That's the point I'm trying to make. There are more precise ways of stating this. I'm just telling you the rough story. Okay, so another question that is of interest is to generate all possible tilings. And how do you generate all possible tilings starting from the all horizontal tiling, right? And how do you we have an exact formula to count them, but that does not mean I know how to generate them, right? So one way of generating is to start with all the horizontal dominoes, and for every 2 by 2 block, that is 2 parallel dominoes, you flip them, make them 2 vertical dominoes. Now here is a mathematical question. Can I get all the domino tilings if I do this operation systematically starting from all the all horizontal domino configuration? So let's look at this example. When m is 2 and n is 4, I start with this all horizontal. Well, I can flip, let's say, these two to get this tiling. I can flip these two to get this tiling. I can flip these two to get this tiling. Remember that we did the calculation for n equals 5. We saw n equals 4. We saw that there were 5 perfect matchings for the ladder graph. This is the identical thing. And how do I get this? Well, I have already flipped this. Now I flip this again. So I've gotten everything. Now the question is this a coincidence? Does it only happen when m equals 2 maybe? Does this happen in general?
Follow the same method and continue for all of them.
Yeah, you continue as much as possible. I mean, you could imagine a situation where you get stuck, where you can't change any more tilings, and yet there are some remaining that you can't get to. It's possible. But I mean, it might have been possible, but there's a theorem that this doesn't happen. So for m equals n equals 4, you can look at it. I mean, you can get from any tiling to any other tiling using only these moves. Just flip something here, flip something there, flip something there, and you get. So if you pick any two tilings, you should be allowed to flip both ways, okay, not just vertical to horizontal, but the other way around also. So it is a mathematical fact, and there's a theorem that says that you can get from any tiling to any other tiling this way. It doesn't say how many steps it requires, maybe it takes a very large number of steps, but it's possible.
What's the kind of theory you want to?
So there's a whole theory. So this is mainly due to Castelline, whose name I mentioned. So all these graphs, if you so basically we are doing perfect matchings of grid graphs, and their grid graphs are bipartite. There's an entire and they are planar. So for planar bipartite graphs, there's a full theory. There's an exact formula which is a determinant, and you basically have to analyze the determinant. So yeah, so there is a there's a large body of work now. Since 1961, people have worked with this a lot. Yeah, I'll mention some more things. Okay, so coming back to this counting formula, this lovely and strange product formula that we had before, this fellow, you see this 4 to the mn here, right? But there's like m times n products here. So if m and n are very, very large, let's say a billion each, how large is this? How does this grow with m and grow with n? That's a natural question that people ask. And so instead of this, there's one would like to get a feel for how large this thing is. How does it grow with m and n? And you see it takes some work, but you can show that this is approximately this c to the 4n squared, if you take the 2n by 2n squared, where this c is an explicit known constant, which is e to the g over pi, where g is Catalan's constant. So you take the alternating reciprocals of the powers of the odd numbers. So you get, this is a known constant. It's not it's not believed to be related to other constants like e and pi and the Euler number. These are all believed to be distinct, but no one has proved it. Okay, so I mean these questions are very, very hard. So, but this is a known constant, and it turns out that this grows exponentially, super exponentially in n, but exponentially in the area. The area is like 4n squared, right? The area of the 2n by 2n squared is 4n squared. So it's some constant to the 4n squared for very, very large n, where this constant is this. So in other words, if you divide f2n by c to the 4n squared and take the limit n going to infinity, you will get 1. Okay, that's the sense in which you have to interpret this. So this constant is sometimes called the degree of freedom. Okay, and this degree of freedom is a measure of how hard it is to find a tiling. Okay, the larger this number, the easier it is to find a tiling. So for us, for the n by n thing, it's 1.3385 roughly. Okay, so this is tilings of rectangles. Since I'm running short of time, I'll finish with tilings of Aztec diamonds. So this is another family of regions that are of interest for various reasons, and I won't go into them. So what is let me describe what these sets are. Okay, so take the staircase of length and height n. Okay, so take this staircase. I'm drawing it here. This is a staircase of length base 3 and height 3. Okay, all my staircases here are the same base and height. So you take that staircase, take a vertical reflection of it, and then take a horizontal reflection of that. So when you reflect this, you get this whole thing, and now you reflect that to get the bottom. So it's 4 copies of the ladder, all of whose centers are connected. The apices, if you wish, are connected here at the center. Okay, so these are called Aztec diamonds, and a priori, why should you care about this, right? I mean, this is some funny region. I mean, somebody came up with it. Why should you bother to waste your time with it, right? That's a question you might ask, and I'll show you why. You might want to think about this. So, when it's 1, there is just a single block, so 4 copies of that block. When it's 2, it's like this. 3 is like this, and large one is like this. So you want to tile. Again, we want to tile them with dominoes. Okay. So how many tilings are there? This one looks familiar, yes? This is the same as a grid. The simple case is a grid. So how many tilings are there? 2, the vertical and the horizontal. Why don't you try to tell me how many are there for this? Huh? Not even close. Let's start with the all horizontal. So there's a horizontal with this, 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 this. Okay. Now slowly start to flip. Huh? Okay, since it's a long day, it's been a long day, let me just show you the answer. It's actually 8. Here are all the 8 of them. So here are all horizontal. First flip this, then flip that, then flip the, no, then you can't get to this directly. You then flip both, then flip the one in the center, then you can flip this, and then you can flip that, and then you can flip both. Okay, so you get it. Okay. Okay, 2, 8. So what? Let's look at the next few numbers. So somebody did this on the computer. So this is what they found. Is there anything that strikes you about these numbers? Exactly. Sorry? All powers of 2. 2 to the 1, 2 to the 3, 2 to the 6, 2 to the 10, 2 to the 15, 2 to the 21. It's absolutely unlikely that such a thing would happen if you pick some random region, right, and let it and scale it. There is something very interesting going on. And what are these exponents? 1, 3, 6, 10, 15, 21. These are exactly the triangular numbers. If you add 1 up to n, you will get the triangular numbers. So this is 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, etc. Right? So the number of domino tilings of the Aztec diamond is exactly 2 to the n plus 1 choose 2, or n times n plus 1 by 2. Okay. This is also because the number of subsets of an n set is 2 to the n. There is also the number of subsets of 1 up to n choose 2, n plus 1 choose 2. But there is no simple way of connecting these two, right? So there is no known bijection, no known simple bijection. Okay, so how many squares are there in the Aztec diamond? So you have 2 in the first row, 4 in the second row, all the way up to 2n, and then you repeat backwards. So twice 2 plus 4, etc., which is 2 times n plus 1. So the number of tilings is this constant c to the 2n plus 1, there should be a parenthesis here, which should be 2 to the n plus 1 by 2, right? This is I'm claiming, I have not proved this to you, and the proof is not easy, so I am not going to give it to you. So what is, how do you get c? Well, c is just whatever is remaining, is 2 to the 1/4, right? So if you take c to this power, the area of the Aztec diamond, just like we had 4n squared for the 2n by 2n squared, we have 2n times n plus 1 for the Aztec diamond of size n. So we get this constant, which is 1.189, whatever it is, and for the square, the degree of freedom, whatever, was 1.33. So, somehow in some sense the square is easier to tile, and there's some sense in there's some precise meaning for this easier in parentheses, okay. But this is what the calculation says. Now let us pick a large random tiling. So you remember what a large random tiling was for the square, 40 by 40 square, and I emphasize that each part looks the same pretty much as every other part. Now here is a large random tiling of the Aztec diamond. Can I say the same thing? No, right? These things are almost certainly horizontal. I mean, there is a large part here which is horizontal, there is a large part here which is horizontal, large part here which is vertical, large part here which is vertical, and in the center there is a bit of a mess, but these things are fixed. So by a random tiling I mean I list down all possible Aztec diamonds and I toss a coin and pick one at random. Toss a huge coin with many sides or whatever, throw a die with many sides and pick one, whatever it falls on, okay. So what is the structure here? So this is called the Arctic circle phenomenon. So let me illustrate what this is. So if you take a large random tiling, just like I told you, it's extremely hard. Are we? Can I have 5 more minutes? Okay, I'll finish in 5 minutes. So if you take, if you toss a coin 1,000 times, it's extremely unlikely to get all. I mean, it's virtually impossible to get all heads. Just like that, it's virtually impossible to get all of them horizontal or all of them vertical. But you see, this region is so constrained. If I have a single horizontal over here, that will force all of these guys to be horizontal. The entire row will be forced, because this will force this will force that, this will force that, all the way, and similarly on this side. So a single thing here can change the character of the tiling completely, and so those are extremely unlikely. So most of the tilings have a large number here which are frozen in this way, large which are frozen in this way, and large, etc., etc. And it turns out that there is a curve here that separates the region which is frozen and the region which is non-frozen, which can be where there is a lot of fluctuation, where things can be of all different types. Okay, and this property is called the Arctic circle phenomenon, and you are supposed to think of the Earth. So you are supposed to think of these as the poles, and so these are the frozen regions, like the Arctic and the Antarctic circle, so the tundra or whatever, and this is the gaseous region. So you can also think about it in terms of materials. So this is solid because it's an ordered lattice-like thing, and this is on the boundary is a liquid region, and in the center is a gaseous region where things are more random. Okay, so this is called, and so there is a curve which separates the two, and so the Arctic curve, the curve that separates it is called the Arctic circle, because just like the Arctic circle, on Earth separates the frozen and the temperate region. So the Fields Medal in 2006 went to Andrei Okounkov for studying these things and their connections. So there are very deep connections to representation theory and algebraic geometry, which I don't know much about. So the Fields Medal is the award given to in mathematics. It's like the mathematical equivalent of the Nobel Prize. So the next one is going to be announced next week. So it is announced once in 4 years, and a maximum of 4 people get it, and the condition is that everybody has to be less than 40 years old. So it's very, very prestigious. So the limiting picture, in fact, for the Aztec diamond is that this thing is exactly a circle. It need not have been, but it is exactly a circle. So it really makes sense to call it an Arctic circle. Okay, so I think I'm running short of time, so I wanted to tell you something about tilings of hexagons, but I think I'll skip, and so thank you for your attention.
Thank today's speaker. Let's clap once again for